Hello, everybody who are listening and watching this. It's just the beginning of 2022, and I want to wish all of you a great and happy New Year.
Hi, Paul. Happy New Year.
Hello, and Happy New Year to you.
I'm Jingkun, a PhD student in John Diffley's lab, just next to yours, here at the Francis Crick Institute. I also represent Sparkx, a researcher-led organization that aims to promote cross-disciplinary and cross-border innovation. So it's my honor to be here with you on our first ever episode of the 0 to 1 podcast.
Well, thank you for asking me to do the first one.
Thank you. So I saw in the news that you just were awarded the Companion of Honor. So were you excited about this award?
Well, it was unexpected, I must say. It's an award for 45 people maximal in the UK, and it covers the arts, the sciences, politics, and the like. So artists like David Hockney and actors like Ian McKellen and so on. So I was very happy to join their community.
Yeah. And you have so many titles and honors already. So let's try to find out how you went from zero and to who you are today. Okay, so my first question to you, what is your 0 to 1 story? It's a quite big question, so maybe let's start from when you were a student.
So to say how I got into science and how I was interested...
I want to ask, were you a good student in school?
I wasn't a good student at school. I was very erratic. I didn't come from an academic family. My parents, who turned out to be my grandparents because of my birth story, but they were working class. So my father worked in a factory as a fitter, and my mother was a cleaner, in fact. And so I had no academic background, and it was a bit of a difficult for me when I went to school initially, and I didn't pass all the exams well, and I couldn't get into university either. In fact, I applied for university. I was rejected, largely because I didn't have a qualification in a foreign language. I'm not very good at speaking foreign languages. I apologize for not speaking any Chinese, for example. And so this meant that it was a bit difficult. I worked as a technician in a lab, in a brewery actually, Guinness Brewery, for a year because I couldn't get into a university. Eventually I was let in, and the more I went up the ladder in education, the better I became. So I did well at university and came near the top of my year, and then did a PhD. My first degree was in Birmingham, my PhD in the University of East Anglia in Norwich. So they weren't particularly famous universities. But I never was a fan of exams. I was never very good at examinations, and I became much better when I stopped having to do them and just started research.
Okay. And I heard you failed your French exams like 6 times.
6 times. So the examination that I had to pass to get into a university was a language exam. I took French, and I did manage to fail it 6 times. And it's a simple exam, and I've never heard of anybody failing it 6 times. And so I think I have a world record in failures.
Okay. So what do you think makes you so good later in science?
I think I'm driven by a curiosity, a very intense curiosity about understanding how things work. My particular interest is how living things work. I study the simplest entity that can be thought to be alive, a cell. I'm very interested, obsessed really, in understanding how cells work, and it's my passion is really just understanding how things work. And I think that's the drive I've had, which is important if you're a researcher, because so many failures occur during research. At least if you're doing something important, you don't understand. And therefore you have to be resilient, and you have to be able to deal with things not working and yet keep going. So I think it's a combination of curiosity and resilience of just keeping going.
Okay, I'm very interested in your discovery of the gene called CDC2. I know it has a quite funny story. It was actually a discovery from the rubbish bin?
Well, partly, yes. What it was I'm a geneticist. I worked with yeast. I looked for mutations in genes that I thought were important for cell reproduction. That's the process of the cell cycle. And this was quite some years ago, I identified maybe 30 or so genes important for cell cycle. One of them was this gene called CDC2. And what was key about it is that CDC2 came in different flavors, different mutants. Mm-hmm. And one was a complete loss of function, which meant that cells couldn't enter into mitosis. But another a version of it, another mutant allele, was one that's advanced into mitosis prematurely at a small size. So that meant that it was advanced into mitosis, suggesting it was important as a rate-limiting control for going into mitosis. And that is the mutant that I isolated, and it was covered on a plate covered with fungus, and that's the one, as you rightly say, I threw in the rubbish, and then came back later, recovered it, and it was that particular mutant that identified how important this gene was for controlling the cell cycle, because it was a rate-limiting step for mitosis and cell division.
Okay. Would you say you were lucky at the time that you retrieved from the rubbish?
Completely lucky, and I have to say it's not the only thing I've been lucky with. I've been lucky with quite a number of different things, and you have to follow where your luck goes. You have to follow where nature leads you in some respects, and you can't think of everything before you see it. And sometimes people approach experiments and research thinking they know the answer they're looking for. Bad thing to do that. You look and see what nature gives you, and then you work out what it means and what the answer is.
So I want to then refer to your commentary recently made on Nature. You said biology must generate ideas as well as data. So do you think there is a lack of ideas in biology?
I'm not sure it's so much a lack of ideas. Though I do think that we do need to think about the ideas. And I think one of the problems we've got here is biologists like to describe lots of details and particulars. I mean, if I was a 19th century biologist, time of Darwin, you'd collect beetles and describe each individual beetle species. Today we sequence genes, and it's the same mental makeup to do that. But it is not enough just to describe. It is also important to use those descriptions to work out how things work, to lead to understanding, and that requires ideas. And as we've seen in recent years, the last half century, a rapid and huge expansion of the ability to collect data. This has meant that ideas have got pushed a bit out of the corner because everybody is working on how we can accumulate more and more data. And once they've done that, they move on to something else. And the purpose of data is to produce ideas. And the purpose of ideas is to produce understanding. And to stop with data is not science, it is simply collecting beetles.
I see. So how would you say people should generate ideas?
I think they have to think about what they're doing, not simply how to do it and to do it well, which is important, but also why they are doing it and what it means. And they should also think about when they get observations that they did not expect, not to simply reject them because it doesn't fit with the idea of the data they were accumulating, but what that might mean as a new idea that counters what people are thinking now. And I'm always most excited about that possibility, that the data brings forth an idea that nobody yet has thought of. Usually it's wrong, usually it doesn't go anywhere, just sometimes it does.
So we can get into the unknown unknowns, I guess.
Exactly.
But what if your ideas are wrong? Like you could have a perfect hypothesis, and it never works. Sometimes it never works in science.
I'll tell you something I think about it. You have to be the biggest opponent to your own idea. Everybody thinks when they have a good idea, they should support it. They should find data to enhance the idea, to make people believe it. Now, I know, of course, that happens, but the really critical data is data where you try and destroy your own idea. And that means you both have to love your idea and also attack your ideas. And it's only if it survives all these attacks that it becomes an idea that's worth having. But, of course, what that means is you destroy your own ideas. And that means you have to be very resilient to be able to deal with that. I mean, because you have a great idea, you think this must be right, you do the experiments, it's destroyed. Then you have to pick yourself up from the floor and keep going. And that's why you need to be persistent and resilient.
So that is the ideology of Karl Popper.
It is.
Do you recommend the book of Karl Popper to everybody?
I think Karl Popper, who was a philosopher who did much of his work here in London, at the London School of Economics, I once wrote to him, actually, when I was a student, because I was thinking of giving up experimental science, because I didn't think I was very good at it, because I kept destroying my own ideas. I hadn't fully realized that's exactly what I should be doing. And I thought about moving into the philosophy of science. I didn't do that. I'm very glad I didn't do that. But what I did do was read a number of his books, and I read also books that interpret him. And if somebody in China wants to know more about Karl Popper, I recommend the books by Peter Medawar, who wrote a very popular version of Karl Popper, now 30, 40 years ago or even longer, which is very understandable. And I recommend every student should read that, because Karl Popper, for me, is very important for the philosophy of science and research.
So do you think scientists should be given enough freedom to just play around, and maybe they will encounter something unexpected?
I think we've got to recognize science is a spectrum. And when you're at the end of what I call discovery science, just discovering how the world works, what you should do is identify good scientists and let them release on the problems they want to study. And their own curiosity will take them forward much better than top-down direction. If, however, you're at the other end of the spectrum, which is trying to work out how to use your science to apply to a particular problem, like solving a disease or making a crop grow better, that has to be more top-down, because you're trying to deliver an outcome that you've already identified. So science operates in different ways. The way I work is at the discovery end, and I give a lot of freedom, not only to myself, but to all my students and postdocs. They have a lot of freedom to pursue what they think is interesting. But if I was trying to make a drug, you can't have the same freedom. You have to have an objective and an aim in mind.
Yeah, more like an engineering approach.
Exactly. It's the difference between what you might call the pursuit of natural science and engineering or medicine.